Today we're going to start the temperature and heat lesson. This will be in two parts. The first part will be more of a lecture explaining temperature and heat and the relationships between them. And the second lecture will be problems. And I'll put the problems at the end of this lecture if you want to see them ahead of time. Alright, so let's go ahead and get started with temperature and heat. So temperature and heat, two different terms. Lots of times they're used to mean the same thing, but they really don't mean the same thing. We need to understand how they're similar. We also need to understand how they're different. So temperature. Temperature is the measure of the average kinetic energy of the atoms or particles. So it's really based on the kinetic energy equation, 1/2 mv squared. Two things go into this, the mass and the speed of the particles. But really we're talking about the particles. We're not talking about like a table doesn't have a higher temperature than a pencil because it's more massive, right? We're really talking about the atoms or the particles that are moving around. Um, so there's two factors that go into this. But for most things, if we're looking at it, the mass tends to not change. So usually it's the speed, right? If we're talking about something, we want to warm it up, we don't add mass to it because that doesn't make sense because it's still the atoms or the particles we're talking about. We just make those particles go faster or slower. So for example, we pump in some gas molecules, and the whole time we're pumping in, the temperature is not going up. Why? Because we're not changing the average kinetic energy of each particle, right? Some are going a little faster, some are going a little slower, but we're talking about the average. Now, let me actually back that up for a second. When we pump it in, we'll see it's going 300. We add heat, and then we automatically start to see these things going faster. When they go faster, the temperature went up, right? The other thing we could do this is if we pump in particles of smaller mass in there, these red ones now are particles with smaller mass, well, both the blue and the red are at the same temperature, but they're definitely not at the same speed, right? The smaller particles, particles with less mass, are going faster, and the particles with more mass are going slower, but they both have the same amount of kinetic energy, therefore they're all at the same temperature. Now, this idea of temperature being kinetic energy and lots of times temperature having to deal directly with speed or speed squared, factors into a lot of different things. If we want to lower the temperature of something, we don't have to figure out how to make it colder. We have to figure out how to slow down the atoms, right? And again, if we want to raise the temperature of something, same thing, right? We don't have to figure out how to make it hotter. We just have to figure out how to speed up the atoms, right? And that really opened the door to a lot of things that we take advantage of today: air conditioners and refrigerators and stoves and all these other things, right? They're really based on how to speed up or slow down the particles more than how to make things hot or cold. But if we understand what temperature is, then we can look at this, or we could apply this to different phases, right? And there's more phases out there than these three, but these are the basic ones, and these are the ones we should know. We should know what a solid is, what a liquid is, and what a gas is, right? And each definition changes slightly. So a solid is a substance with a constant volume and shape, right? It takes up the same space all the time, and it keeps the same shape all the time. A liquid is different. It has a constant volume also, right? It takes up the same space no matter what. If I had 50 milliliters of water and I dump it on the floor, well, it's still 50 milliliters of water. If I pour it into a bowl, it's still 50 milliliters of water, right? It still takes up the same amount of space. But what it does do is it changes its shape, and it changes its shape to fit the container that it's in. The last phase is a gas, and a gas is a substance that changes volume and shape. It does both, or both change, and it does that to fill a container. So we could watch gases expand if we put them in a big container, or we could watch them contract or squeeze into a smaller amount, right? So volume is something that constantly changes in gases, and the shape absolutely does too, right? So it changes volume and shape to fill a container. So as we look at these, and from things we've understand like H2O, it has ice, it has water, it has steam, but those change as temperature changes, and pretty much all, not every material, but most materials do the same thing, right? At the lowest temperatures is when they're a solid, and then the middle they're a liquid, and then at their highest temperatures is when they're a gas. Well, I mean, that factors into speed also, if we think about it. So I turn this simulation on, I have these molecules and they're moving. Now this is a solid, it has a definitive shape and volume. As I add a little energy to it, they go a little faster, right? And these atoms are being held If you remember from chemistry, there's bonds holding these things together. There's ionic and covalent bonds. Some of these bonds are very strong, some of these bonds are very weak. But as we increase the speed of the atoms, then they'll start moving faster and faster and faster, and they'll start breaking some of the bonds. Now I'm into a liquid, right? So some of the bonds that were there that were holding it together as a solid weren't strong enough to hold these atoms in place as they start moving faster, so some of the bonds break. Now we get these atoms going even faster, and now we have it turned to a gas, right? Now some of the bonds that were there holding it together as a liquid, now those bonds start breaking because again the atoms are going even faster and these bonds can't hold them. So now we have a gas, right? And these particles are now not really attached to each other at all because they're just simply moving too fast for that, right? So we can go through the different phases as we speed up the atoms, and that's absolutely something that we'll be looking at. So again, temperature. Temperature has to do with kinetic energy, and it also has to do with speed because speed is related to kinetic energy. Heat. Heat is something very different. Heat is the flow of energy from high temperature material to low temperature material, right? It is a flow of energy. One thing gains energy, one thing loses energy. If we remember from our last chapter of energy, there's two ways that we can give energy to something else now. We could do it through work. If you do work on something, it gains energy. The other thing we could do is heat. If heat flows into something, then it gains energy, right? So heat and work are the two ways that we transfer energy, right? Heat has very specific rules, though. It goes from a material at a high temperature to a material at a low temperature. Um, and really, this is work. It's just work on a different level, right? Work is when you apply a force to something and make it move. So if we envision that there's these molecules moving, they're moving very, very fast, and we put them in contact with these molecules that are moving very, very slow, well, the faster moving ones are going to start hitting the slower moving ones and then making them increase speed, right? So it's still really work, but it's work on a scale that we really can't see. But different than energy, or I'm sorry, different than temperature. Temperature is the measure of the kinetic energy of a material. Heat is the flow of energy. Energy is moving from one thing to another when we talk about heat. Um, and it moves from a high temperature to a low temperature. Now, we see some of these differences in our everyday lives. If you took two things out of the fridge, let's say you took a can of soda out of the fridge, and then you took a bottle of water out of the fridge and you touched them both, right? I pretty much guarantee that the can of soda will feel colder in your hand. Now, is it at a lower temperature? No, not really, right? It feels colder because when you touch it, there's a lot of energy flowing out of your hand into that can, right? And when we feel things that are hot or cold, what we're feeling is heat, right? If you touch something that's hot, that means energy is flowing into your hand. If you touch something that's cold, then that means energy is flowing out of your hand, right? So if we go back to this can and this water bottle, we touch them both, the can's going to feel very cold, and the water bottle's not going to feel so cold. Are they at different temperatures? Not really. They've both been in the fridge for a long time, so they're both at whatever temperature the inside of the fridge is, but one of them allows for a lot of energy to flow, the other one doesn't. So one feels colder than the other, even though they're at the same temperature. Now, let's look at these two things. When we look at this next one, it is listed as time, but what we have is we have an object of a high temperature. Something's burning, right? So it's at a high temperature. And then we have ice, which is at a very low temperature. So heat's going to flow from the high temperature material into the low temperature material. As we look at this graph, though, it's listed with temperature versus time, which is fine, but really we can call this bottom one, if we didn't want to call it time, we call it heat, because the longer it's there, the more heat that flows in. So even though this graph listed as time, I tend to list it as heat. Because constantly while this candle is burning, heat's flowing into the ice. So if we run this simulation, we start to see the things that we talked about. We're going to see some phase changes, and we're going to see some temperature changes. So right now, even though it's not really showing it, the molecules are going faster and faster and faster. On the graph, we see the temperature go up from -20 to 0. At 0, something occurs, though, right? We were at the speed where if we add any more energy, the molecules start to break apart. And now I no longer have a solid, I have a liquid, right? And we also notice that while it's changing over, it does it at a constant temperature. This is important, and mathematically, it's very, very helpful to us, right? As this phase change is occurring, temperature doesn't change. Now, when we look at it, all we have is water, And as more energy flows into the water, again, we see the temperature going up and up and up, and we see the molecules going faster and faster and faster. But then we reach a point right now where, again, we are going through a phase change. We're going from water to steam, or going from a liquid to a gas. But again, while that happens, it happens at a constant temperature. So the whole time the water's boiling, it doesn't get hotter, doesn't get to a higher temperature while it's boiling. It stays at a constant temperature, because now the energy we put into it is causing the molecules to break apart and turn into steam. Now, this last part isn't really a great simulation because it's not showing something realistic. But if we just had steam and we kept pouring energy into it, we would see the temperature of the steam go up. And that part's true. It's just a simulation didn't match. A simulation kind of matched with the real world, which really wouldn't have this happen. Because one of the things we saw is if we keep heating up the steam, there we go. If we keep heating up the water and turn it into steam, where does the steam go? The steam leaves, right? So I would argue that most people in the world have never really seen steam. And one reason why we know we've never seen steam is because steam's dry. It's not wet. If you're cooking on the stove and you see steam rising out of the pot and you run your hand through it, your hand's going to be wet, which tells you one thing, wasn't really steam. But what happens is the same thing that this simulation, the left side of the simulation, is showing. If we start boiling water and the molecules start leaving, where do they go? Well, they go away. So as soon as they leave the heat source, they're not gaining energy anymore. They're actually doing just the opposite. They're cooling off, or they're giving its energy into the atmosphere. So if something turns into steam, or we have water that turns into steam, as soon as it leaves the heat source, well, it turns right back into water. Now, it may be small droplets of water or very small droplets of water floating around in the air, but it's not really steam anymore. Okay, but going back to this graph that we have, there's a few things we could see. We could see when we went from ice to water, there's a horizontal line. It happened at 0 degrees, and it didn't change temperature while this was happening. We also see when it went from water to steam, and again, it happened at 100 degrees, and the temperature didn't change while this was happening, right? So we get a very distinct shape, and just by looking at it, we could see when we had a certain material that was changing temperature, and then we could see where the temperature was constant, we were changing phase. Now I'm going to bring up that graph again. Graph looks something like this, right? So we have ice and the ice temperature is going up. We have a change of ice to water. We have water and the temperature is going up. We have the change of water to steam. And then if we could trap the steam and keep it right at the heat source, we would see the temperature of the steam going up, right? So all our lines, 2 are horizontal phase changes, and 3 are lines with a positive slope, temperature changes, right? So we're going to mark these. These 3 that have that are lines going up are lines with a positive slope. We're going to mark with a circle right there. Oop, don't change on me. There we go. Let's add another one. Right there. And then we're going to add another one right here. Now the shapes are a little weird, right? Let's make this one a little more of a circle if I can. Or I'm not going to sweat it. There we go, good. So these 3 parts of the graphs that we marked with circles are places where we have a change in temperature. As energy flows, temperature changes, right? Phase didn't change in these spots. This is when we had an ice or a solid. This is where we had water or a liquid. This is where we had steam or a gas, right? And as energy flowed when we're there, temperature went up or down, right? And what's important there is what we're dealing with is areas where there's a specific heat. And we could say as heat flows, temperature changes. So all of these circled areas are areas where heat flows and temperature changes. What changes, or what affects how much the temperature changes? Well, a few things done. The mass of it. If we're trying to heat up a lot of water, well, we're not going to have a big temperature change. We're trying to heat up a small amount of water, there's going to be a bigger temperature change, all other things being equal. The other thing that matters is how much heat flows, how much energy goes into that material, or comes out of it. And the last thing that matters for how much the temperature will change is what type of material are we heating up. It's a lot easier to warm up a metal like, let's say, copper than it is to heat up a plastic or even water, right? Some things are easy to heat up, some things are hard to heat up. So these are the things that affect the temperature change, which gives us this equation right here. This is a specific heat capacity equation, which says the change in energy equals the mass times the specific heat times the change in temperature. We'll talk about specific heat a little more, actually on the next slide, but three of these should make sense. The heat flow equals the mass of the material times specific heat times the change in temperature. And what's specific heat? What does that C represent? Well, the specific heat is the amount of energy required to change 1 kilogram of a material, that should be of a material, by 1 degree Celsius. Remember, a 1 degree temperature change is the same as a 1 degree or a 1 Kelvin temperature change. And again, if you want to look at temperature scales, you should. They're on the website. So specific heat is a measurement of how much energy it takes to change 1 kilogram of material by 1 degree Celsius. Now, if we go back to this graph, these flat areas are something different. They wouldn't use that equation because these flat areas don't have a temperature change. So it doesn't make sense to use an equation that deals with temperature change. So this is a different equation because different things are going on, right? Right here, well, that's something different, right? That's not a temperature change. That's a phase change. And over here, same type of thing. Here's not a temperature change. Here's a phase change. So it's not going to be the same type of equation, but while these three use the same equation because we're dealing with temperature changes, these two use a different equation from the other ones, but they use the same type of situation or the same type of equation. And that's places where it deals with phases or changes in phase. So that's what we're talking about. Talking about is latent heat. This is as heat flows, phase changes, right? So if we had ice and it was right at 0 degrees and energy went into it, it would change the water. On the flip side, if we had water at 0 degrees and we took energy out of it, it would change back to ice, right? So what determines how much material goes through a phase change? Well, two things do. Number one, how much heat flowed. Number two, what type of material are we talking about? And again, some things melt easier than other things or turn to a gas, from a liquid easier than other things, right? So the material definitely matters. And these are the only two that really affect how much material goes through a phase change. So the equation for that section is this. The heat equals the mass times the specific latent heat. Sometimes I just call it the latent heat, which is perfectly fine too. So again, Q is the heat, M is the mass, and then we have this measurement, which is latent heat. It's not much different than specific heat, but specific heat dealt with a change in temperature. Latent heat deals with a change in phase, right? So latent heat is the amount, I'll say it because it's not written down. Latent heat is the amount of energy required to change 1 kilogram of a material from a solid to a liquid. Or it could be the amount of energy required to change 1 kilogram of a liquid to a gas. And I'll say a little more about that. We can break it up into two groups. We could have the latent heat of fusion, which is when we're going from a solid to a liquid, or we could have the latent heat of vaporization when we go from a liquid to a gas. But in both cases, it's how much energy required to change 1 kilogram of that material. So you're never going to have to memorize these for me, but there are a few that you should write down and you should know. Any of the values that have to do with water or H2O, we should know those values because those are the ones that are going to be used in the most, right? So we have two specific heats. Change how much energy does it take to change the temperature of ice? How much energy does it take to change the temperature of water? And then in latent heat, the same type of thing. We go from ice to water. How much energy does it take to change a kilogram from ice to water? How much energy does it take to change a kilogram from water to steam? The other thing to notice while we're finishing this one up is how big those values are, right? Last chapter, you were calculating potential energies and kinetic energies of all these different situations. And a lot of them were real world type situations where the values you calculated were realistic to those types of situations. They were in the thousands, they were in the hundreds. Sometimes they were only like around 10 or 12 joules of energy. But if we look at these numbers, we can really see that it takes an enormous amount of energy. So sorry about that. These numbers are so big that it actually factors into a lot of different things, right? It takes an enormous amount of energy to heat up 1 kilogram of water by 1 degree, right? It takes 4,180 joules just to heat up 1 kilogram of water by just 1 degree. If we think about how much it takes to heat up a lake or to heat up the ocean, right? It takes enormous amounts of energy. right? And then also, right, to change things, to melt an iceberg, to change it from ice to water, again, enormous amounts of energy has to go into it to make this happen, right? That's part of what's kind of buffering us from global warming, right? If we think about it, we have these gigantic bodies of water, and it takes an enormous amount of energy to get them to change by 1 kilogram degree Celsius. So as we gather more and more energy in the earth because it's trapped here, right? The temperatures on our planet aren't going up too high, but they're not going to go up too high too quickly because it takes enormous amounts of energy just to heat up the water. So all that excess energy just keeps going into our oceans and raising the temperature more and more and more. On the flip side, um, if we get to a point where we're not trapping so much energy, all that energy is going to slowly have to leak out of the oceans, right? So we're not going to see temperatures drop too quickly either, right? All of these high numbers really serve as a buffer for us. Okay, so we've hit on the basics of temperature and heat, and now it's going to be time to look at equations. So you could certainly pause it at different spots so you could see, so you could try these problems. But then I'll put them up again before I solve them in the next lecture. So here's the first two problems we should be able to try. How much energy is needed to lower the temperature of 5 kilograms of water from 76 degrees to 32 degrees? The next one, we have 3 kilograms of ice and it's at minus 12 degrees when we have 10,000 joules of energy added to it. What is the final temperature? So those are problems 1 and 2. Problems 3 and 4, how much energy is needed to take 2.5 kilograms of ice at minus 20 degrees Celsius to water at 75? So now we're doing multiple things, right? We're heating up ice, we're changing from ice to water, we're heating up water, right? So this is a multi-part problem. And the last one is 2. We have 2 million joules of energy and it's added to 7 kilograms of ice. What is the final condition? What temperature is it at? What phase is it at? So these are the questions that we should be able to answer if you understand what I did in this last lecture.